of an ideal gas, a system containing 1 kilogram of ideal gas at 5 bar pressure and 0.02 meter cube volume executes a cyclic process comprising the following three distinct operations. One, reversible expansion to 0.08 meter cube volume, 1.5 bar pressure, presuming pressure to be a linear function of volume, that is P is equal to A plus BV, reversible cooling at constant pressure, and reversible hyperbolic compression according to law PV equal constant, according to the law PV equal constant. This brings the gas back to initial condition. This brings the gas back to initial conditions. Sketch 1. Sketch the circle on a PV diagram. And 2, calculate the work done the network, the work done, and heat transfer. Okay, so as usual, note the parameters and let's look at the solution. Start by giving, we are giving M equal to 1 kilogram, P1 equal to 5 bar, V1 equal to 0.02 meter cube, V2 is equal to 0.08 meter cube, P2 is equal to 1.5 bar, we want to sketch the PV diagram. So we start by following the process. State point 1 at 5 bar follows a linear reversible expansion to state 2, 1.5 bar, pressure in bar, and volume in meter cubed. And then it follows a constant pressure process to state 3, and then follows a hyperbolic process by PV equal to a constant back to its initial state. So now we have V2 is 0.8, V1 is equal to 0.02, V2 is equal to 0.08, and V here, V3 we would find. So with that, remember this is a law of A plus B, V is equal to P. So let's start from state 1 to 2. We call up our formula for work done 1 to 2 is equal to integral 1 to 2 P dV. P is given by that, so we would have also to get what A and B, what this constants A and B is, before we can use the PV formula. So to do that, remember that we have a straight line, so we can form two equations immediately. The first equation is at state 1. At state 1, when P is equal to 5, when A plus B times B 0.02, and again P is equal to 1.5 when A plus B times 0.08. So if I solve these two equations, equation 1 and equation 2 simultaneously, how might I obtain A and B? I will have A to be equal to 6.167 and B to be equal to minus 58.33. If you want to do this, you remember you can solve simultaneous equations by two basic methods, substitution or by eliminating coefficients. So what you want to do is to knock out A and then find B, and then from B find A. Okay, so noting that we could get these two solutions, we could now write the PV equation as P is equal to 6.167 minus 58.33 times V. So this P formula, remember we've noted that you have to have P in terms of V to be able to evaluate this integral. So let's do that again. We want to evaluate that integral. We will have integral from 6.167 minus 58.33 V from 1 to 2. So if I do that integration, I'm going to have, first of all, that the integral becomes 6.167 V minus 58.33 V squared over 2. All from taking the definite integral from state 1 to 2, that is V1 and V2, which are 0.02 and 0.08. So if I substitute these two values here to evaluate the definite integral, I will have the work to turn out to be 19.5 kilojoules. Remember, we are going to multiply P. The value of P is in bar here, so we must multiply this equation by 10 to the power of 3 because of the units of pressure, which is in bar. Sorry, by 10 to the power of 5, please. Noted. So, this is the work done by the system in process 1 to 2. Let's look at process 2 to 3. Now, I want to point out something. You can pause the video for a while and think about how you might calculate this work done without trying to use this PV formula. You recall that PV, the area under the graph, stage 1 to 2, will give us the work done. So if you want to use that method, we can therefore write something for us. So we're interested in this area, okay. So we call that the formula for the area of this shape basically becomes, if I name it 1, 2, let's name it with letters A, B, C, D, back to A. So if I say area A, B, C, D is equal to, the formula for finding the area of a trapezium is equal to the 1/2 times this width and the sum of the two parallel lines. So I can have 1/2h A plus B. So if we write down, so we know that this is the formula for calculating the area of a trapezium. In this case, we have our h to be DC, which is 0.08 minus 0.02. So I will have 1/2 into 0.08 minus 0.02 times the sum of the two parallel. So I'll have that 1.5 plus 5 times 10 to the power 5. So this will give me 19.5 kilojoules. So we've arrived at the same thing using two different methods, but the same concept of area under the PV diagram for stage 1 to 2. If we consider stage 2 to 3, stage 2 to 3, the work done to 3 is equal to, of course, 2 to 3 is a constant pressure process, so that's P2 into V3 minus V2. Okay. So, but remember, we do not have this V3. How do we find it? We call that this process 1 to 3 is a hyperbolic expansion process. So I can write P1 V1 is equal to P3 V3. So V3 is equal to P1 V1 over P3. And that will mean P1 V1 is equal to 5 times 0.02, 5 bar times 0.02 over P3, which we have as 1.5 times 10 to the power 5 again, because it's in bar. So this cancels out. So this turns out to give us V3 as 0.0667 meter cubed. Now I have V3. What I can do is to put this into the equation. So W23 becomes P2, which is 1.5 times 10 to the power 5 into 0.0667 minus V2, which is 0.08. So if you do this, you notice you have a negative figure of minus 1.995 kilojoules. Now we have this work. The next and final work is the work 3.1. So W3.1 is equal to, we know we've seen this before, P3 V3 ln of V1 over V3. And if I put the parameters right here, we're going to have this W3.1 as minus 12.05 kilojoules. Now, because it's a circle, I will take the net work for the circle. So that becomes W net is equal to W12 plus W23 plus W31. So W12 was 19.5 minus plus minus 1.995 plus minus 12.05, and that gives us 5.445 kilojoules. Now this is the W net, which also means for a circle, the cyclic integral of the Q is equal to the cyclic integral of the W. That means the heat transferred in the circle is also equal to 5.445 kilojoules. Next time, we'd want to look at the application of first law to flow processes. All we've looked at this time was to non-flow processes, that is closed systems, processes that have no matter crossing their boundaries. In the next session, we'll be looking at systems that have matter crossing their boundaries, that is the flow system or